Okay, well, today we're going to start the topic 2, the second major topic in Industrial Systems Engineering 630. Now, while there is a textbook chapter, I believe it's chapter 4, that covers basics of human factors with vision, I should note that I made all of these slides with the help of input provided by Dr. Copa before that book was made. So while it covers the similar and all relevant topics, you may not see a whole lot of parallels here with the current material here, but everything in the lectures are what I will be examining on. Everything in the lectures that are also covered in the book, supplementary. All right. So let's get going. All right, so the vision lecture is actually broken up into 7 parts. And so hopefully each of these is at a digestible sort of amount of information. But we're going to start off with talking about the hardware behind the process of vision. And so 2.1, the basics of sight and eye anatomy. Now, I'm going to do this also when we talk about audition. But I think it's interesting from a technically minded person to understand that the experience of vision starts with a physical property in the physical universe, just like with hearing, actually, just like with all of our senses. There is some physical manifestation of energy in the universe, and our 5 or however many you count senses are tuned in to making a perception out of that energy. So we start with that energy for vision here, and that's electromagnetic radiation. So if you are studying, physics, and you learn about electromagnetism and the propagation of waves of electromagnetic radiation, we're talking about light. So light is, oscillating electrical and magnetic dimensions. Don't worry, you don't have to remember that too much here, but if that's interesting to you, might call back from physics a little bit. But we're mostly interested in one property of a electromagnetic radiation wave, and that is the wavelength. So, or conversely, the frequency. But they talk about waves of light in terms of wavelength. So the peak to peak, and it's in measurable distance over which those peaks occur. And essentially, this property of the physical nature of electromagnetic radiation, aka light, is how our eye interprets color. So we're going to talk about I think it's topic 2.3, how color vision works in terms of how anatomically the different receptors on the back of the eye combine their input to present to the brain something that gets interpreted as color. But we get a lot of nice philosophical, deep conversations around that. What does it mean to be blue, for example? But in essence, whatever blue is to you, which might be different from me, might be different from anybody else, and we'll never know, it is consistently associated with a certain wavelength of light. So in nanometers, the range of roughly a little smaller than 400 nanometers until a little larger than 700 nanometers basically represents the entirety of the visible spectrum. Okay. Now, I always like to point out the scale of electromagnetic radiation relative to other the same form of energy. Literally, electromagnetic radiation exists over orders of magnitude in higher frequency or smaller wavelength, and on the other side as well. So gamma rays, which made the Hulk, Bruce Wayne, what is it? Bruce Banner turned into the Hulk because of gamma rays. Those are very high energy electromagnetic rays. Why do you know it's higher energy? It's got a faster frequency. Okay. And so the closer okay, so yeah, basically the shorter the wavelength, the higher the energy in order to produce that much oscillation basically in this radiation. So gamma rays make you into the Hulk. X-rays, we know, are high energy radiated particles, but maybe before this lecture, you didn't realize, oh, we're talking about the same form of energy, just different bands of frequency / waveform that go with each of them. Here's a cool factoid, right? So if this is that little tiny sliver of electromagnetic radiation that our eye is tuned to, look at the entirety of the world of energy that's all around us all the time that our eyes are not tuned to. So these energies can be picked up, radio waves. Obviously, we have hardware, we have technologies that can detect and use these. The human eye does not. But this just kind of puts in a very small example of how infinitesimal our human senses are to interpreting the energies of the universe around us. So I always like to have that moment to think, oh, everything that I know as visible items exist in this very narrow band of reflected energy. And that's just one of my senses, but there's almost infinite energy around us that our senses are not sensitive to. So we have no experience of them. So not to blow your mind too much, but yeah, I like to do that. Take ISCN 635 if you want to have more of the philosophical, deep conversations around this. All right. So yeah, roughly between 360 nanometers and 760 nanometers. If you are outside of that range as a beam of light, the human eye cannot detect it, but a lot of very common mechanical eyes can. So hang on one second. I got to grab something. Okay, good news. Since my recording room is also a TV and video game room, we have a TV remote. And this is an infrared TV remote, as are most technologies that are wireless remotes here in 2022. And I want to just show you that when I push a button on this, and you can do this with your own remote at home, I got nothing here if I'm looking at it with my naked human eye. But if I use a mechanical device like a camera, so my GoPro camera that is recording this lecture is, and most cameras are, you can get this on your cell phone probably as well, they are sensitive to a slightly wider range of light than the human eye. And so remotes very commonly use this band of light, which is a low energy output form of light that travels a great distance and doesn't bother the humans that are sitting around in the dark trying to adjust the volume on their movie. So very cool. So if you ever wondered, why can my camera see this and the human eye can't? It's because we're existing just beyond typically what a human eye is sensitive to. If I remember, something like 900 something nanometers is your typical infrared, 900 and something. There is a typical value there. All right. So, all right, moving on here. Great. There's their example, right? All right. Okay. Now, brief departure into a philosophy class. What does it mean to see something? Now, I'm going to have, there's like an abrupt transition here between what I can talk about the human senses providing to the brain and what yours and my experience of seeing something. There is this leap between anatomically what we can describe, physiologically what we can describe, and no, this is as natural as anything. I am experiencing the visual environment around me as reality, and I'm not, so to some extent, I want to say, look at the complexity of the process that delivers sight to our cognitive system of our brains. And it's fascinating, and seems effortless, seems, it's kind of an amazing thing that translates everything into our continuous streaming video input to our brain, which is the visual input from our entire visual system. All right, here we go. So electromagnetic radiation strikes something. This is where seeing starts. So, it's this cup. So it's in the universe, it's everywhere. It's coming from the sun, It's coming from other, light sources. The light in this room, just like any light source, is electromagnetic radiation. And that is, a property of applying energy to whatever light emitting element is there. And so that light then moves at the speed of light, and it strikes something. And some of that light reflects off of it. Some of it is absorbed. When we talk about absorption of that energy versus reflection of that energy, now we're talking about something that matters in terms of what is the color of that object, how bright does it appear, how much information is available for the human eye. So the property of reflectance is something that'll come up, in a later subtopic here. So light strikes it. It reflects off that object, some of the light, not all of it. Some of it reflects off of it. And that light is then available for another surface. And if that surface is the back of a human eye, so the light travels in all directions, reflecting off of this object. And if some of that light passes through the cornea, the pupil, the cornea is the first layer of skin on the surface of the eye. The pupil is the hole. The lens is the focusing anatomical element. And the retina is the receiving matrix of cells at the back of the eyeball. So I'll show you more close up in that in a moment. So once the light has reached what we call our visual receptors, so receptors are a specialized type of neuron that transforms, here we go. Receptors are a special type of neuron that transforms physical energies of electromagnetic radiation into neural signals. So I want to say like it's a chemical energy transformation, but I'm not sure about that. But in any case, light strikes the retina sends signals via neurons, patterned signals, to ultimately the visual cortex. So this is the optic nerve that is the wire coming out of the back of your receptor eye. All of the nerves of the retina basically deliver their signals here and then down this channel. You may know this from earlier class in biology, neurobiology or something, but there is a crossing of the streams, so to speak, in the visual system. So what is appearing to us on the right side of our exterior space is actually processed on the left side of our body, and on the left side of our visual cortex here. And this happens because it crosses through this X-shaped sort of anatomical structure they call the optic chiasm, CHIASM. So chi as in the Greek the Greek letter X, optic chiasm, there it is. So the left, and it's actually not right eye goes to left brain. It's right side of space in both eyes. See if you can see the blue coating here, or sorry, I guess the left side of space here is processed, on the right side of the eye, and then is, on the right side of the brain here as well. So, and the visual cortex is where all of the input, I think I've got that here, in the visual cortex, the light input from the retina, but there's other input, not just light-based input, that determines our visual experience, our perception. So the input of our ocular muscles, and I'll give one example, ready? So if you can see my eyes right now, I'm crossing them, and the tension I feel, I'm actually looking at my microphone right now, the tension I feel in my eyes is input to my visual cortex that tells me the light that's processed on the retinas of those two eyes needs to be interpreted as a near object because of the ocular tension, the tension in the ocular muscles. So both in the position of my eyes and then also in the muscles that tune your focus, the plane of focus. We'll talk about those in a moment. But each of those are input to the visual cortex, ultimately all contributing to that emergent perception of sight. Okay, so it's an amazing combination of sensory inputs that gives us this elegant, whatever, ultra HD visual experience. All right. Okay, old anatomy textbook picture of an eye. So some of the key anatomical features that you'll want to know about for quizzes and exams, right? The cornea. So this is our very first layer of skin. This is the protective coating over the surface of the eye. And without this, you have essentially, you know, at least through air, you can access the eye. There's a hole here underneath it, right? And there's a very soft tissue here. So this is an important protective layering. Now, those of you like me, I know I'm wearing goggles right now, but like me, I about 20 years ago, I had LASIK surgery. Some of you may have had it as well. My wife's had it very successfully. I've had it with moderate success. As you can see, I'm re-goggled. But what happens during LASIK surgery, there's more on this in a later topic, but they actually peel back, or they temporarily sever and then fold back this top layer of skin, the cornea. And that allows reshaping of the material underneath the cornea, so that when the cornea reheals, it's a very highly healing surface as well. Then there's a new curvature to the eye, which matters for how light is resolved on the retina. Okay, so far that was like a foreshadowing, I guess, you know, whatever. Went too far ahead there. But that's the cornea. You need to know about that. So the protective layer of skin there. Then the hole, right? So the pupil, the dark black, and it looks black to most of our experience because essentially there isn't a light bulb behind it, but it's a black dark hole. Okay, so it's like looking down into a sewer. That's a bad example, but there's no light beneath it, so it appears black from the outside. However, you know, like if you go to the eye doctor, or, you know, hopefully you don't have too many people shining lights in your eyes to look at this. It's not generally a good thing unless it's the eye doctor. You may be able to see some of the interior of the eye with a bright enough light. But otherwise it appears black because it's a hole. It's literally the device, or the element by which more or less light is let into the eye, and then thus available for focusing on the retina. All right, so the pupil's the hole. There we go. The lens. Now this is tissue, but it's a bizarre sort of like it's a semi-transparent, flexible, jelly-like tissue. Okay, and it can deform and then return. Like, think of it like, I mean, maybe I do think of it this way. I'm not sure this is a good example, but Jello, right? So with Jello, if you ever wiggle Jello and you're looking at it, you get like this distortion of the light that goes through it. Very common. I mean, that's an analogy that I have with what the lens provides. So it's obviously not Jello, but it is a similar sort of you know, a dynamic with that. Now these muscles around the lens, that's what these are right here. What do we got? These, like the ciliary body. I guess I don't have the muscles linked here, so you don't have to know them, I guess. But those muscles there expand and contract the lens, and that's the tension you feel. Now do this right now with me. Look at your fingertip. I guess look at the one without the Band-Aid on it, and bring it closer and closer to your eyes. You can even just use one eye. Just use one eye. Get it closer and closer and keep trying to resolve it. And at some point, you'll feel the tension is too great and you can't resolve it to fine detail anymore. It blurs out. And what you are finding is essentially the limits of these muscles right here to flatten, or what is it? No, it's actually it's actually to scrunch up and cause more curvature in order to resolve things that are closer and closer to our eyes. So that tension is, you know, the limits of those muscles occur at the close end, not at the far end. It's always relaxing to look really far away. Even if you can't make out things at a distance, those muscles, how much do I have to focus to resolve this? They are most relaxed when you're looking as far away as you can, or what we call it at infinity. All right, so that's the lens. Now, the lens itself is not a muscle. It is a transparent tissue that there are muscles that deform and change the shape of the lens in order to focus light at different distances. There it is, the retina. You can't see it so well back there, but this is an array of neural receptors that respond to specific wavelengths of light with a certain amount of energy, and the relative input from different types of receptors on the retina is how we basically recreate color imagery. All right, so there's your 4 keywords, right? Now, I think most of us will be familiar with a camera. This is not a digital cam. Well, it might be a digital camera, but this is a more traditional, like, photography art camera, maybe a single lens reflex SLR camera. And I want to kind of make a couple of parallels here for those of you who might be photographers, either, by hobby or otherwise. All right. So 2 basic functions of the eye that very much relate to how do you get a clear image with a camera. So the first is, how much light do we let into the eye? And that is controlled by the pupil diameter. How dilated or constricted is the pupil. And there are a lot of things that affect that pupil diameter size, but most prominently is the amount of light in the environment, and how much are you trying to see, with the given amount of light in the environment. So very similar to adjusting the aperture of a camera in terms of how much time is a shutter frame open, it's going to let in more light. So it's not exactly like a diameter thing, but it is about how much light do we let into the imagery here. Accommodation, this is when those muscles of the eye change the shape of that lens in order to bring things into sharp focus for us. And by sharp focus, it's essentially saying we're going to get a nice, crisp, non-noisy, basically a focal point on the retina itself, and not past the retina or in front of the retina, so that a distorted image would reach the retina. And so when things look blurry, it's because there's a distorted image reaching the retina, not a nice, crisp, perfect focal point on the retina. And you'll see more of that in a later topic here. All right, so accommodation. So pupil diameter changes. Accommodation. Sorry, the volume. But accommodation is about that focus. So if I see something close to me and then I bring it into focus like this, I have essentially changed the shape of the lens so that light at this, from these locations are more precisely focusing on, on that point at the retina. Okay. So the diameter, I mentioned that the diameter of the pupil is affected by a number of things, but its primary focus here is how much light do we let in. And so, yeah, you'll find this if you want to do a little experiment on yourself, shine a flashlight in just one eye, and you can get this sort of an effect here. Your eyes do act independently to an extent. They're also affected to some extent, but mostly you can do this. This is a dilated pupil. Sometimes if you go to like the eye doctor or something, they may give you a certain eye drop that medically induces that state. The reason they do that is because now the hole is the largest. And so if they're shining a light in there, they can see the most into your eye, and they can literally see your retina. And I have a picture of my own retina that you'll get to see if you tune in next time. So constricts to let in less light, dilates to let in more light. The reason that's important is you need just the right amount of light. You need the right difference between the lights and the darks, the foreground and the background, the important and the extraneous, in order for your eyes, for your visual system to make out detail. So it adjusts to basically whatever the lighting levels are. If it gets brighter in this room, my eyes will constrict for a little bit naturally. If it gets darker in this room, my eyes will naturally dilate. So if I am trying to seek visual information, your eyes will adapt to the amount of light that's present, and trying to get just the right tuned level so that things come into focus with good with good clarity. If we don't have enough light, can't resolve things. If we have too much light, we also can't resolve things. So we need that light and dark distinction And we can get that somewhere in between those two. I think it's topic 2.6 talks about contrast and the need for the distance between, for the difference between light and dark aspects in making a very visually clear image. Okay, cool. So side note, because we're talking about pupil diameter, I use in some of our research, we use something called a pupilometer. And that is measuring the diameter of the pupil using image-based methods. But we use this when we're having people in like our driving simulator or doing some other task as one measure of cognitive workload. So as it turns out, when people are thinking harder, they're doing more, they're exerting more cognitive effort, their pupils naturally dilate, and they dilate to a measurable extent. The interesting, or the counter argument to that is, well, if I just turn the lights on and off, you know, the pupil will move this much, whereas cognitive workload makes them move, you know, fractions of a millimeter sometimes. So it's harder to measure, but if you have the right equipment, you can, you know, you can get some indication of people's cognitive activity based on the size of their pupilometer, their pupils. How interested you are in something. So pupilometry is also used in things like marketing research. So here we're going to show you a bunch of pictures. We're going to see where your eyes go, and we're also going to see what your the diameter of your pupils do. And so typically, if you think of it like, oh, I see something I'm interested in, I want to absorb as much as I can of that thing, your pupils dilate to some extent. So it's an indication of interest. It's an indication of pleasure or desire to some extent. And so, you know, I always talk about, oh, well, you know, that image of your nice kitty that wants something. And so what is this, you know, the doe-eyed sort of stare? Well, this is essentially showing another organism the most, this is showing a kitty that is looking at me, and with the dilated eyes, it's communicating to me, a different organism, that that thing thinks I'm very, very interesting and probably loves me. And so there is this, you know, oh, you know, I'll help you, little kitty, or, you know, obviously it can be any organism. And so the emotional state also is conveyed to some extent through a person-to-person interaction or a person to another, you know, organism interaction. The pupil diameter does to some extent communicate interest. So, you know, you can use that however you want, hopefully not creepily, but human to human, you may also see interest in somebody by the dilation of their pupils. Seems like a dangerous thing. Don't take that too far. All right. All right, so this is section 2.1. Thanks. Turn in for section 2.2, where we go into more detail on the anatomy and the function, the physiology of the retina. Thank you.